You know, when we think about the signs of death, there's one that everyone knows, something that's become a key piece of the puzzle in pretty much every forensic investigation: rigor mortis. So, in this explainer, we're going to break down exactly what causes this postmortem stiffening and how it becomes a silent witness for investigators. Let's get into it. So, here's what we're going to cover. First, we'll get a handle on what rigor mortis actually is. Then we'll dive deep into the biochemistry behind it, what's happening at the molecular level. After that, we'll map out its pretty predictable timeline and see how investigators use that as a kind of clock. And finally, we'll look at some crucial imposters, conditions that can look a lot like rigor and might just mislead an investigation if you're not careful. All right, let's start at the beginning. What exactly is this unmistakable grip of death, sometimes called cadaveric rigidity? I mean, that's the big question, isn't it? Right after death, the muscles actually go into a state of total relaxation, what's known as primary flaccidity. But it doesn't take long for that unmistakable stiffening to start setting in. And the answer to why that happens? Well, it's found deep inside the muscle cells themselves. Now, here's the most important thing to get. Rigor mortis isn't a vital sign. It's a chemical one. This isn't some lingering spark of life. It's the direct result of the body's molecular machinery just grinding to a permanent halt. It's the moment when death really takes hold at a cellular level. So to really understand this whole process, we need to zoom way, way in. Let's explore the biochemistry of this stiffening and take a look at the incredible molecular machinery inside our muscles. Okay, so in a living muscle, everything is this elegant, energy-driven dance. You can think of actin and myosin as two protein filaments that really want to grab onto each other, which is what makes a muscle contract. Calcium acts like the trigger, telling them when it's time to bind, but the most crucial player for letting go of that grip is ATP. That's the energy that powers their separation, allowing the muscle to relax again. After death, this whole system just collapses. Without oxygen, the body can't make any more ATP. The membranes that hold all the calcium break down, flooding the muscle fibers with calcium ions. This flood makes actin and myosin bind together and contract. But here's the catch. With no new ATP, there's no energy to unlock them. They form this super stable, rigid complex called actomyosin, and the muscle just stays locked. And this quote, it just perfectly illustrates the mechanics of it. Imagine millions of microscopic pistons locking into their cylinders, but with no fuel left to pull them back out. That's exactly what's causing the stiffness we can see and feel on a large scale. And get this, here's a really fascinating detail. Maximum stiffness doesn't happen when ATP hits zero. The rigidity actually peaks when the ATP levels drop to about 15% of what they normally are. This locked state then stays put until the later stages of decomposition start to physically break down the muscle proteins themselves. Okay, so we get the why behind the stiffness. Now let's talk about the when. The timeline of rigor mortis is where all this knowledge becomes an absolutely critical tool for forensic science. This is the classic rule of thumb you always hear about. Stiffening is usually spotted first in these smaller muscles, like in the face and jaw, and then it seems to work its way downwards. It's worth noting, though, that some researchers have suggested this might be less about a top-down pattern and more about muscle size. It's just easier to notice the change in smaller muscles first. But either way, this descending pattern is a pretty useful general guide. Now for the clock itself. This timeline is based on observations in India, which is a great detail because it really highlights how crucial the environment is. A warmer climate just speeds everything up. So rigor typically starts about 1 to 2 hours after death, it's fully developed by 2 to 4 hours, and it can last anywhere from 18 to 48 hours. After that, as decomposition starts breaking down the muscle proteins, the body softens up again in a process called secondary flaccidity. But, and this is a big but, that timeline is not set in stone. Not at all. A whole bunch of factors can speed it up or slow it down. Things like high fevers, intense physical activity right before death, or just a hot environment, they all accelerate the process because they burn through ATP much faster. On the flip side, a cold environment can delay it quite a bit. So understanding this variable timeline is absolutely essential for investigators. How is all this biochemical knowledge actually used at a crime scene? Well, its importance in a medical legal sense really boils down to 3 huge things. First, it's an undeniable sign of death. Can't argue with it. Second, like we just saw, its stage of development gives a rough estimate of the time since death. And third, and this can be the most critical clue in a suspicious death, it tells us about the position of the body. Picture this. A body is found lying flat on its back on the floor, but one arm is stiffly raised in the air, completely defying gravity. Well, that's a massive red flag for investigators. It means rigor mortis locked that arm in place before the body was on the floor, maybe when it was slumped over in a chair. It's powerful, silent proof that the scene has been disturbed. But for rigor mortis to be a reliable clue, an investigator has to be 100% certain that's what they're looking at. So in our final section, we're going to look at the imposters, other conditions that cause stiffening and can really complicate things. The short answer? Nope, not at all. An investigator has to be able to tell the difference between true biochemical rigor and other conditions that might look similar on the surface, but tell a very, very different story. Okay, the most dramatic imposter is something called cadaveric spasm, and the difference is night and day. Rigor is this slow, system-wide process. A cadaveric spasm is instantaneous and localized, and it's so strong it can take immense force to break. So its forensic value isn't about estimating the time of death, but revealing the mode of death. It literally freezes the body's very last physical action. Then you have the environmental imposters. Heat stiffening, which you might see in burn victims, is caused by the muscle proteins literally being cooked and coagulated. It's way more rigid than true rigor. Cold stiffening is much simpler. It's just the body's tissues and fluids freezing solid. The key difference there? If you warm up a body with cold stiffening, it'll go soft again before the normal process of rigor mortis even begins. And this brings us back to that really wild phenomenon, cadaveric spasm. It's super rare, but when it happens, it's like forensic gold. Think of a suicide victim found with a weapon clutched so tightly in their hand you can't pry it loose. Or a drowning victim found grasping weeds from the riverbank. That instantaneous lock provides powerful, direct evidence of what was happening in the final moment of life. And that really gets to the heart of forensic pathology, doesn't it? Rigor mortis is never looked at in a vacuum. It's just one piece of a really complex puzzle, right alongside body temperature, lividity, and all the other evidence at the scene. The real skill is in understanding how all these variables fit together to tell a coherent story, to reconstruct those final, silent moments.